I'm going to talk about Euclidean domains. The main idea behind Euclidean domains is very simple. It is Euclidean division. So what do I mean by Euclidean division? This is something you know from your primary school probably. If you take two integers, m and n, let's say assume that m is non-zero, then we know that there exist integers q and r such that n is equal to qm plus r and r lies between 0 and m, absolute value of m. So we allow here m to be positive or negative. Okay, so this is very useful, for example, in finding the GCD of two numbers. So let me define, we can rephrase this GCD problem in another way. So given two integers m and n, define, I'll call it the ideal generated by m and n. So we'll see this notion of ideal in greater generality later, but right now we'll just look at this as the set. We'll write it as parentheses m comma n as a set of all am plus bn where a belongs to z and b belongs to z. Okay, and we can also talk about the ideal generated by a single element. Ideal generated by m is just am, a belongs to z, all integer multiples of m. Okay, so the ideal generated by 2 is just all even numbers. We can ask what is the ideal generated by 2 and 3. So what are all the integers that can be written as 2 times a plus 3 times b, where a and b are integers. Okay, and the answer to this question is that the ideal generated by m and n is the ideal generated by the GCD of m and n. And the Euclidean algorithm gives a way to find this GCD. So I'll state all this in a somewhat ideal theoretic manner because what we are interested in is understanding ideals in Euclidean domains. So let me start with a lemma. So suppose we have this Euclidean division. So we have like n equals qm plus r. So suppose we have this for n, m, q, r all integers, then I claim that the ideal generated by m and n is the same as the ideal generated by m and r. Well, here's a proof. So I'll show firstly that the ideal generated by m and n is contained in the ideal generated by m and r. So typical element of the ideal generated by m and n is of the form am plus bn. But now n is qm plus r, so I can write this as am plus b times qm plus r, which is a plus bq times m plus b times r. So this is also of the form, if I call this a prime and b prime is b, then this is of the form a prime m plus b prime r. So this belongs to the ideal generated by m and r. Conversely, if you have, okay, so what we've shown is that Mn is contained in Mr. Conversely, if you have Am plus Br, then now R can be written as N minus Qm, so we'll use that. Am plus B N minus Qm, which is A minus BQM plus Bn. So now I can call this A prime and I can call this P prime. So this is A prime M plus B prime N. So we have the other containment. Okay, now let's just do an example of how to reduce an ideal generated by two elements to an ideal generated by one element using Euclid's division. So let's do this with an example. So let's start with the numbers 168 and 49. Okay, so now 168 you can calculate. If I divide by 49, it is 3 into 49 plus, so 3 into 49 is 147, 147 plus 21. So it's 3 into 49 plus 21. So using this lemma up here, what we are saying is that I can replace 168 and 49 by 49 and 21. So the ideal generated by 168 and 49 is the same as the ideal generated by 49 and 21. And now how does 21 go into 49? 21 into 2 is 42 plus 7. So I can write this as 21, 7. And then what about 21? That is 3 into 7 plus 0. So this is equal to the ideal generated by 7, 0, but that's just the same as the ideal generated by 7. So what we've done is we've started with an ideal that's generated by 168 and 49, and we've shown that it is the same as the ideal generated by 7 using this lemma up here. And at each stage we've used Euclid's division. Okay, this kind of thing can also be done with polynomials. So polynomials also admit Euclidean division. Slightly modified. So what you have is that given polynomials, so let's take polynomials in a field. So let K be a field. You can take your favorite field, real numbers, complex numbers, rational numbers, whatever you like. And let's take mx, nx in polynomials in x. And we'll assume as before that mx is not identically 0. Okay, then there exist polynomials qx and rx such that nx is equal to mx times qx plus rx when degree of rx is less than degree of mx, or rx is equal to 0. Okay. I don't know what the degree of the 0 polynomial is. Sometimes we say minus infinity, so that would still work. Okay, so this is the Euclidean algorithm for Euclid division algorithm for polynomials, and we can use this again to describe to reduce ideals. So let's try this with some polynomials. So again, given two polynomials mx comma nx, the ideal generated by them is just px mx plus qx nx, all polynomials of this form, where px and qx are any polynomials in kx. Okay, and we have the same lemma that if you have this equation that nx is mx qx plus rx, then this would imply that mx nx, the ideal generated by mx and nx, is the same as the ideal generated by mx and rx. Okay, so let's do an example here of the same kind. So let's start with the ideal generated by x to the power 4 plus x squared plus x minus 3 and x squared minus 1. I want to know if I can reduce this to an ideal generated by a single element. So we'll do, so why does actually Euclid's division work? It's basically we have a long division algorithm which allows us to do it. So x to the power 4 plus x squared plus x minus 3. So how many times does this go in? I can put x squared here and I get x squared minus x to the power 4 minus x squared. So that cancels off and I get 2x squared plus x. So I put here plus 2 and I get 2x squared minus 2x, and so that's 2x squared minus 2, and so that's x plus 2 minus 3, which is x minus 1. So what we get is x to the power 4 plus x squared plus x minus 3 is x squared minus 1 times x squared plus 2 plus x minus 1. So this is qx and this is rx. So we can replace this ideal is the same as the ideal generated by x squared minus 1 and x minus 1. And now we divide x squared minus 1 by x minus 1. We know that, x squared minus 1 is x minus 1 times x plus 1. So this is the same as x minus 1 comma 0. So that's the ideal generated by x minus 1. So we have this ideal generated by two elements, and using Euclid's division, we've reduced it to an ideal generated by one element. I'm now ready to define a Euclidean domain. A Euclidean domain is a ring R which has the following properties. Firstly, it has to be a commutative ring. Secondly, as the name suggests, it should be an integral domain. So this means that the product of two non-zero elements of R is again non-zero. And the third property is that there is a size function. So it comes with a size function. D from R to non-negative integers such that for all m n in R with m not equal to 0, there exist q and r in R such that n is equal to qm plus r, where the size of R is less than the size of m, or R is equal to 0. So we've seen already two examples of Euclidean domains. Z is a Euclidean domain with degree function just given by the absolute value, and the polynomial ring over a field is a Euclidean domain with the size function of a polynomial is just the degree of the polynomial. Okay, and we've seen, the Euclidean division in both cases establishes this third axiom. Okay, another useful definition to have now is that of a principal ideal. So firstly, what is an ideal? So I'll assume that R is a commutative ring. Though this definition should also be made for non-commutative rings, we'll do that later. So assume that R is a commutative ring, then an ideal in R is a subset I of R such that two properties hold. The first is that I is a group under addition. It's a subgroup of R. And the second, more important property is that for all A in I and for all R in R, A times R belongs to I. So it's not just closed under multiplication inside itself, but it's closed under multiplication by any element of R. So examples. So given any ring R, any commutative ring, and elements M1, M2, Mk in R, then the ideal generated by M1, M2, Mk is defined to be the set of all elements of the form A1, M1 plus AK, Mk, where A1 through AK are in R. Okay, and a principal ideal is just an ideal of the form M for some M in R. So this is equal to all elements of the form A times M, where A belongs to R. So example of principal ideal in the integers is all multiples of an integer M. Okay, and now I'll give you a nice example of how axiomatization works in ring theory. So it's a theorem which now encompasses both polynomial rings and integers, and we'll see a few more interesting rings. Very general theorem which says that every ideal in a Euclidean domain is principal. So we saw examples of how to express ideals generated by two elements as principal ideals when we repeatedly used Euclidean division earlier. But this is a very general statement, and the proof is actually quite simple. So suppose I is an ideal in a Euclidean domain R, and I want to show that I is a principal ideal. So I need to find this element M such that the ideal generated by M is I. So if I is just singleton 0, then we are done, right? Because I can just take M to be 0, it's the ideal generated by 0. Otherwise, I has an element, a non-zero element, and this function D, the size function on R, well, it takes non-negative integer values, so it must achieve a minimum value somewhere on R. So it has a non-zero element with the property that dA, non-zero element, let's say M, such that dm is less than or equal to dm prime for all m prime belonging to I. Okay, and now I claim that actually M alone generates I. And how do we prove this claim? Well, take any element n in I. Okay, I want to show that n is just a multiple of m. Now by the Euclidean algorithm, n is equal to qm plus r, where d of either r is 0 or dr is less than dm. But if r is 0, then we are already done, right? Because we are just saying that n is q times n. Okay, if dr is strictly less than dm, then we also know that n is in I and m is in I, and r is n minus qm, so this is also in I, right? Because n is in I and m is in I, so qm is in I, and so minus qm is also in I because I is an additive subgroup, and so n minus qm is also in I. But then dr is strictly less than dm, which is a contradiction. So I has to be generated by any element of minimal size in it. Let's look at one more surprising example of a Euclidean domain, which is Gaussian integers is a Euclidean domain. The D function here is just a squared plus b squared. I'll let you think about how to prove this. And let me end with a non-example. So we've been working with polynomials with coefficients in a field. But if I take zx, polynomials with integer coefficients, then this is not a Euclidean domain. Why is that? Well, one way to see it is that, well, how would you show that there is no size function which does blah blah blah? But one way to show it is that, well, it's not a principal ideal domain. Not every ideal is principal. Take the ideal generated by 2 and x. Okay, this is not a principal ideal.